Good morning, all of you. I am Dr. Sunil Kumar Yadav, PG Department of Physics, Veer Kumar Singh University, Ara. The topic of my presentation is fluctuating nonlinear hydrodynamics of passive and active systems, a dynamic renormalization group perspective. In this talk, I will briefly compare passive fluid and active matter hydrodynamics and highlights how dynamic renormalization group ideas help us understand their large-scale behavior. The outline of my talk is first I will discuss the hydrodynamic description of a passive incompressible fluid, then I will discuss polar active matter, then dynamic RG, of course, graining and rescaling. Finally, I will discuss the important large-scale results and concluding remarks. Passive fluid fluctuating Navier-Stokes equation. The hydrodynamic description is given by the mass density field and momentum density field. For the incompressible fluid, we take density constant and del dot V equals to 0. The velocity field equation is the Navier-Stokes equation, where the V dot del V term is the nonlinear term, nu naught is the viscosity, F is the random force term. Here the lambda naught is perturbative parameter. Physically it is set to 1. Now active matter hydrodynamics. This is the velocity field equation for the active matter hydrodynamics. The terms colored in red are the terms which appear due to the self-propelled nature uh, of the particles. Here the parameter lambda is non-unity, which indicates that Galilean invariance is broken. Chemical potential mu is expressed in the terms of density fluctuation. These equations are derived in these references from the microscopic Langevin equations. Now here I discuss the dynamic renormalization group ideas. This is the two-step process. In first step, we coarse grain the equations. We eliminate the short wavelength modes. In the second step, we rescale space and time and restore the cutoff. And dynamic RZ studies scaling in both length and time scales. In doing this, we try to find out which term is relevant at large length and time scale. This is the recursion relation for the passive particle hydrodynamics parameter. The recursion relations for viscosity and noise strength D are looking like the same. This is due to the fluctuation dissipation theorem. For the dimensions greater or equal to 2, dynamic exponent approaches to the value 2. Spectral energy density behaves as q to the power d minus 1. In 3D it is behaving like q square, which follows the equipartition theorem. To conclude, passive fluid hydrodynamics is governed by conservation laws and equilibrium fluctuations, whereas active matter hydrodynamics contains additional non-equilibrium terms arising from self-propulsion and energy consumption. Dynamic RZ provides a useful tool for identifying the relevant hydrodynamic terms and understanding the emergent large-scale behavior of both passive and active systems.